morning. This is Ron from the Encyclopedia team. It is with great pleasure today we have Professor Martins to this interview. Thank you very much for joining us, Professor Martins.
Okay, thank you very much for giving me the opportunity to give you some of my thinkings and about my pathway as far as science and technology is concerned. I will be very happy to stay here with you for the next hour or so.
Thank you for coming. So before we dive into your research topic, please tell us a little bit about yourself.
Okay, thank you very much to give me this opportunity. So I have to tell you that I start research in the area of disordered materials. Amorphous silicon was my first topic that I researched, having as my supervisor Professor Walter Speer that won the European Prize Physics due to the work that he did in the field of disordered materials, namely amorphous silicon for applications. And I have had as my supervisor, I have been lucky because it was Professor Neville Mott that won the Nobel Prize in 1977. So this was the grounds of my research and my driving curiosity to make things different. In this pathway, as far as research is concerned, in the area of amorphous silicon, besides working on solar cells, we did the first integrated position sensitivity detectors for exploiting the photoconductivity of amorphous silicon. This was something very important for us. We patented this work, but the target was very limited. The doors of my research really open when we start researching in the area of oxides, and we discovered that we could make it also to behave at if we reduce the amount of material, they could behave similar to a semiconductor, and then we could make the first full transparent oxide thin film transistor, which was, I think, a breakthrough in the research area. And this was at the beginning of the century, followed by the invention of the paper electronics that we patented. Also, we did the first memories that today people call the synapse memories. This is our patent, and this is something that I believe will impact on all these matters in the future. And also we registered the green electronic for the future is something that we registered in 2005, because we always believe that the green technology and sustainability could be something very important. But along this pathway, I always was a devoted for promoted advocacy in the area of materials. I was the former president of the European Materials Research Society, also the president of the Senate of EMRS. Then I became also a member of the steering committee of the European Materials Platform, where I still belong, also on the EMRI, which is something devoted to the field of materials for energy in Europe. Among all this, my pathway, I became also the president, which I am still the president of the European Academy of Science. So this is something that really matters to me. And also I'm a former member of the Scientific Council of the European Research Council, which in my opinion is the best scientific council in the world, devoted to look for talents and to promote breakthrough and disruptive actions through all the world, because ERC aims to attract talents, whatever they are, and bring out of the box ideas that otherwise could not be really very well developed. And we are very pleased as a member of ERC that the last vaccines have been invented by people that got grants from ERC. And also we are proud that we have only 10 years, but we have already more than 8 Nobel Prizes out of our fellowships. Also, presently, I'm the running president of the International Union of Material Research Society, which has a long impact. So we try to bring together all globally the scientific community thinking in the materials for a plethora of applications. This is my the way where I look the things, where I think that we could really promote talents. So I'm very proud that inside my lab we have talents. We have people with DRC grants thinking different and looking for the new perspectives for the future, which I believe science should be like that. Science is to serve the citizens. It's just not to give pleasure to me. It's to serve the citizens and create new things and new opportunities to make better the welfare and the comfort of the people. That's in general what I think.
Such an inspirational quote at the end, and I'm sure you are glad of how many titles that you are holding, and I am really glad that the achievements you guys have been done.
Yeah, thank you very much. But life is like that. If you don't give, you don't receive.
Got it. So could you please tell us a little bit more background on material science?
Yeah, okay. In the material science, as you could see, we start by looking for disordered materials. And when we move for the oxides, the idea was that as the structure of the oxides is completely different from the covalent semiconductors, it means that disorder will not affect the figure of merit in electronics, which is the mobility. And this is really, we could reach this because we could get mobilities which are 2-3 orders of magnitude larger than amorphous silicon. And then, of course, we could go beyond one of the barriers that we have, one of the limitations in the amorphous silicon. So the idea was how I could try to connect it and be inspired to go farther in using low cost and fully recyclable materials, as the oxides are much better than silicon. Then what we try to see is that on this global world, we have to look for how we reduce the amount of materials that we have to use. And in this respect, of course, we have to think on nanomaterials. And also we have to look for technologies, what we call green technology, which means that we have to make everything that traditionally in electronics we make using clean room facilities in a quite broad environment where everyone could be acceptable and can use it. Then, of course, we started looking for low-cost technologies using low energy out of the clean room facilities as it is traditional on silicon technology. In this respect, of course, we have to reduce the amount of materials, get functionalized surfaces, and then we starting researching on nanomaterials. So because if we go downscale, we can make the same type of applications as on upper scale, and we can even control, we can engineering the band gap of materials. We have a very simple example. Gold is yellow, but when you go at the nanoscale, you can get it red. So it means that I can control the band of the materials, and this is something that is engineering, and it means that I can really scope and try to push further this type of application. So my research was focused on exploiting low-cost technologies and try to think in new functionalities for the materials. More recently, of course, this is what we did with the paper electronics, because it's the most green material that we know, and we can functionalize the paper surface. And for instance, for a plethora of applications, if I can give life and I can make things happen on the paper surface, it means that for diagnostic applications is the easiest and the most suitable application that we can do, because at the end of the essay, I can just burn the paper. While for silicon, chip on with silicon, this cannot be done. You have to recycle, and the costs are very, very expensive. This is an idea that we exploit, and recently, with my wife, Elvira Fortunato, we could get this golden medal from the United Nations, because during the COVID times, we could use a very easy way using this paper-based diagnostic platforms to test and to identify the COVID. This great guy that makes us suffering, but also make us to think different and try to find new ways and new discoveries. So In this respect, I have been centered my activities in looking for new applications for the functional materials at a nanoscale. This is something that we have to exploit because we still have some limitations. For instance, the first active matrices based on oxides that Samsung is using, they use our idea, our concepts, and we have a common patent with Samsung. This was what makes us very, very, very well known in the world, because the first displays using oxides are based on this technology that we are proud to be aligned with what Idea Ozono first proposed, followed by John Wager. But we were the first really trying to make everything at low temperatures and using disordered and not ordered materials. This makes all the difference, completely all the difference on costs on the technology to be exploited. And as far as technology is exploited, we believe that printing-based technologies are a very good way to move further. We are doing this because this is a very low-cost technology. That's why we have to discover new inks, formulate new inks, trying to find water solvents that could impact, try to see as far as how I can control the behavior of these materials at a nanoscale, either N-type or P-type, try to make the first CMOS devices, making logic gates based on these low-cost materials, try to identify memories, how I can capture the information, try to transmit the information, just trying to design antennas on any type of surface. This is something that impacts in our lives very recently, is to using the laser-induced graphene, where I can write on the surface. Whatever you have a surface where you have graphene, I can write, I can transform the surface, I can make it conductive, and then I can design without adding material. I used to call this is a subtractive-like technology, because I don't add materials, as people are saying, I'm adding materials to make something different. In this case, I'm just trying to use the same surface, but I transform the surface to make things happen. And this is something very important, and goes to a different pathway that we are exploiting, is that if I can transform the surface of the materials, if I can really give different functionalizations to the materials, it means that I can transfer complex functions to be performed by exploiting the multifunctionalities of the material. This is something that we believe what this means that I can transform materials, making it the insulator, semiconductor, or conductor, and in this prospect I can integrate it in the same surface all the functionalities that I need to make integrated circuit using low cost. And in this respect, I think that this could be a very good avenue for the future, because everyone knows the impact that we have on the silicon technology, on the microelectronics, on the crisis of microelectronics, but for a broad range of applications, namely in the car industry. We don't need the silicon chips as we are using and exploiting today. We can use cheaper materials, fully recovered materials like the oxides, or maybe hybrid. Even in some cases, we can use organic semiconductors. And in this respect, we can overcome the limitations that today we have with supplying silicon for a broad range of applications. So I believe the next step that we have to give is go for chip-less foundries. Chip-less foundries. This is the name that I gave. And I also use a different concept that I used to say, research in the field of materials, because materials are the activators and the accelerators of all the transformations that we need, whatever the scope and the application that we envisage. This is definitely, we have to look for the materials. We have to look how we can exploit this type of materials. And in this respect, I have this concept that is the metro station. In each station, we can change the lines. What I mean by this is that what I can use the same materials for different type of application. This is how in the station. So I can develop materials and then I can see what could be the most relevant field where I can exploit it and take advantage of this. So my passion is by sure look for the materials as the key factor for the party of science and technology. What I also used to say is there are no party of science and technology without materials. We need materials, and this symbiotic or this evaluation chain that goes from the raw materials to the applications means that we have to take care. We have to look for circularity, how I can reuse and reutilize materials, and then it means that nano is something that is very, very important. Not because I can use for different type of applications and exploit new functionalities, but because it's a way also to reduce by orders of magnitude, 3 or 4 orders of magnitude, the amount of material that I need for an application. Look, for instance, for a thin film transistors, if I go to a nanoscale, maybe I can improve by more than 1 order of magnitude today's mobility. So this is in the field of nanoelectronics, of course. But anyhow, I need nanometers of material, while today's technology, I need micrometers. So it's 3 orders of magnitude. So it means that I can do the same by less. And this is what we have to do, make more with less. And this is my dream for the future is how we can exploit materials using for different concepts and how I can really, in some way, like molding material for the needs that impact in our lives for the future. And this is, of course, functional materials is my dream, is my beach.
All right, the future sounds really promising. I mean, who doesn't like efficient use of our energy, right?
Yeah.
So,
yeah, this is true. Absolutely true and correct. I remember that when we started looking for what we call transparent electronics with my wife, Elvira, it was the time that we have this movie that Tony Cruise appears. It was that it appears it was like a spy, and he appears in a display in a window, and he tries to move with the windows and try to see what he could get it. And at that time, it was a fiction. Today is a reality. And as I believe that it will be a reality, even the movies from Harry Potter on this journal that they make everything. You have a display in the web page. So we will make electronic paper or paper electronics to be a reality. Not the e-paper is a fact because it's a display, but we can make it paper to be a display functionalizing with all the applications. And I believe we are very, very close to do so. And even for security applications where I need to make the tracking, I can make this using oxide. I don't need to use silicon. I believe that the foundries of the future will be for a sustainable electronics will be based on that. Of course, silicon, we need silicon. I'm not against silicon, but we can complement for a broad range of commodities where indeed we don't need silicon to do so. And we can use more affordable foundries that can be promoted and could serve the welfare for the applications where today is just for conservative. We are still using silicon. We can substitute silicon easily, but we are conservative. People to change the mindset takes some time, and is our obligation to change the mindset of the people.
Intriguing. That makes me wonder, what are the challenges that you are facing in the current situation in order to make the future come to reality?
I think that the great challenges that today we have is some limitations on this type of materials that we can process at low temperatures. And one of the bottlenecks and for electronics applications is is the mobility. And in this respect, we have to go to downwards. We have to go to nanoscale, because the mobility also depends on a geometric factor. And if I can decrease the today's size of the transistor by 2 or 3 orders of magnitude, means that I will increase the mobility in the same amount. So this is one way to go, is to go for nano and try to see how, and this means to use nanotechnologies and see how we can go it. This is in the electronics. The other field that I believe we have to go, and there's a good direction, is on the solar refineries for the future. We have to integrate a different type of green technologies. Photovoltaics per se is not an answer. We have to use piezoelectricity, so mechanical transformation of mechanical on energy, thermoelectricity, photovoltaics, everything together to make the solar refineries of the future. This is a challenge for the future. People now are centered on hydrogen, could be a solution, a dangerous solution, but is a solution. But I think that there are still a pathway that we can exploit on the other side, and we have to look together very carefully on this matters. And in this respect, I believe that the great challenge is not to reduce the cost, for instance, on photovoltaics. It's impossible, because unless we make slaves to work for us, we got the minimum limits for photovoltaics. What we have to increase, and this is the great challenge, is the conversion efficiency of the solar cells. In this respect, it means that we have to go for new architectures of the solar cells. We have to go for new design and exploiting photonics. In this respect, very recently, last year, my group, we could design and propose a new design for solar cells where we could almost double today's efficiency. This is fantastic. At least in the scientific community, we got more than 2 million of viewers on this paper, because it's a new ideas. People are really scarcity of good ideas, not to make the same. And of course, it was an idea. It was we simulated the data, but this is how we move. So I think there are 2 ways: look for green and sustainable materials, how I can exploit and go further either on the electronics applications or on the optoelectronics applications. So this is, I believe, the directions. And for this, I think we have to change our mindset and try to see what are the green, what I call green materials, or materials that we have that are abundant, easily to recycle, and using less and less energy. So this is one thing. Technologies where everything is processing using very low temperatures, then it is a plus. It reflects not only in the cost, but also on the CO2 footprint. And also try to see how I can exploit it, new concepts, and exploit new multi-functionalities of materials for security applications, for energy, for electronics, for health, as key, and also in the agriculture. More and more, of course, I forget something which is very important, is sensing. Today is in the future, you may have sensors everywhere to control the environment, the water quality, the human body. So we have to introduce sensors, and we have to communicate this information via this very simple electronics with an antenna that I can design on the surface. We may have displays on textiles. I may have written controllers, cardiac written controls that I can transmit directly to a receptor, and then everyone can know my status for a lot of casualties that we have on the vascular application. I believe this could be a plus, because it means that you can act very, very fast if a vascular accident happens, for instance. So I think that the health quality is something that could benefit of all these developments on materials in the electronics, as well as the comfort of the people. And moreover, more and more, you need these small commodities. It's impossible to stop all this. Look, more and more, you need to have smart tags. You giving comfort. So you are producing billions and billions of these things. Can you keep it doing in silicon? Are you able to recycle everything on silicon? It's impossible. You have to change your mindset.
Thank you. There are just so many applications with material science, so it makes me wonder, what is your next move for this research from you?
Okay. As I told you from the beginning, the next step of the research is try to exploit multifunctionalities and use very low cost technologies like LEAG, where I can write directly on the surface my circuits. It means, for instance, for microelectronics, I don't need to use clean room facilities. I don't need to pattern an integrated circuit. Very simple. I need minimum 6, 7, 8 steps, while with LEAG technology or printing technology, we just have one step to do it, and I can make it out of the clean room. So our next step is to exploit LEAG applications and going, as I told you, for nano electronics targets. And all this, if I can make it and reduce the size, means that I can integrate multiple functions on textiles. Remember, it means that I can give life at a nanoscale. Look at the book of Julius Verne, where you can have not only to exploit space differently, but you can exploit inside our body by using smart nanoparticles that you can inject and could promote different type of applications. This is a dream, of course, but I believe that will become true in the next 5 or 10 years.
The future sounds promising. So last but not least, is there any acknowledgement you would like to make?
Oh, of course, I would like to acknowledge something, because I born in Africa, and in Africa we have a proverb that say, if you are fast, go alone. If you want to go farther, come together. And of course, I have to thanks to my team, a fantastic team. They believe, and we come together. And in my team, of course, I have to thanks my wife, Elvira Fortunato, because I share with her a lot of things together. And she has been really impacting in science together with me, and we make a team. And this is what I really believe is on team. And of course, I would like also to give a very very grateful to all in the world to which I have been working, going from the European Material Research Society members to the IUMRS, which I believe to be a global society that aims to share science to a broad community, and science is globally and is free. And in this respect, I'm very thanks to all the people that I'm working together to make a better science to all, to serve all.
We wish you and your team all the best for your future endeavors. And thank you again for joining us, Dr. Martins.
Okay, thank you very much. I hope that you can give steps to bring better life and promote creativity and breakthrough among young talents that we have spread in the world. And if I can help to do so with my motivations, this, I think, is a victory for me. Thank you very much.
I sure hope Harry Potter one day comes true.
Yeah. Okay. Okay, thank you very much.